Okay, let me first tell you about doping. Okay, so what is doping? So doping. So doping is the process of adding impurity to a pure semiconductor crystal like silicon or germanium crystal so as to improve its conductivity is called doping. So doping means to increase the conductivity by adding impurities impurities like arsenic or antimony or maybe indium or gallium to pure form of semiconductor. So that is doping. So silicon, we know that silicon or germanium is a semiconductor. There are semiconductors like in the periodic table. We know that in the group number 4 we can know that it is silicon, and germanium, and tin also. In the periodic table in group number 6 we also know that there is selenium and tellurium. Okay, so we have these semiconductors, pure semiconductors. However, there are semiconductors like arsenic. This is not actually semiconductor, but if we combine with like silicon, so it become good semiconductors. Okay, and also if we combine like boron or a antimony. Okay, so these are like metalloids. These are not actually semiconductors, but they are metalloids. However, if we combine with silicon, and they can be very good semiconductors. So metalloids. So metalloids plus some silicon or germanium. So they are also like aluminum is also metal. Aluminum and arsenite, and also indium and gallium. Indium gallium also is there. Indium gallium, these are all compound. If we combine, so it can be a very good semiconductors. Okay, so we shall proceed on to what is actually the pure form of semiconductors look like. Pure form of semiconductors are called intrinsic. Okay, intrinsic semiconductor. Intrinsic. Though there are numbers of semiconductors like tellurium, celurium, but according to the availability and the silicon, they use it free. MOS, isn't it? They use it MOS. Silicon hi anmang na sa emema chanchu leya hian atam emema. So silicon pure form, we know silicon 4 valence electron. 4 valence electron, and this is silicon, and silicon. Here will be another atom, silicon, another atom here. This is silicon, all joined together like with a double bond. I can show only in this page I can show only a few chain only. So all are joined a double bond like this. This is silicon. All are silicon. So there are no external material, no impurities from outside. Okay, so all are plus 4. Okay, it's as I have told you, silicon have 4 valence electron. So here we have this silicon 1, 2, 3, and here up, or I can show you 1, 2, 3, 4. This is 4 valence electrons, and another come from here from the neighboring. Let's here one from this neighboring, another one from this neighboring. So I made a mistake, so I have to combine like this. This is the double bond. Okay, so it is very difficult to write, but however you can see another one here from coming from here, another one from here. Okay, so from the neighboring atom, one each is shared, and this atom itself have four, 1 2 3 4, isn't it? So this, it's completely filled, electronic configuration 8. Okay, 8 completely filled. Okay, let us look this photo, look this picture. This is a pure form of semiconductors that I have talked about. Instead of here in this diagram, we see that instead of silicon, writing silicon, we see +4 is a silicon. This is a pure form, and it is regularly and beautifully arranged. Okay, so this is a pure form in every place. This 1 2 3 4 5 6 7 8. Okay, 1 2 3 4 5 6 7 8, 8 electronic configuration. This completely filled. This is a pure form. Okay, so this silicon is a pure form of semiconductor, which is called intrinsic semiconductor. Okay, pure form because it is completely filled and there is no excess or extra electron. Okay, this kind of intrinsic semiconductors, its conductivity is very less because there is no much extra electron. That's why it is not very suitable to use. Okay, it is not very suitable to use. That's why we need doping. Okay, doping means in the beginning, as I have told you, it is the addition of impurities. Okay, like arsenic or indium or gallium or maybe antimony. Okay, so now we shall see how it is doped. There are two ways of doping. Okay, there are two ways. We can dope in two ways. Number one is by adding pentavalent impurity. Okay, so by adding pentavalent, that means 5 valency electron. Those who have 5 valency, okay, like arsenic and antimony, which are metalloids. Okay, if we add to this semiconductor, pure form of semiconductor, then we can have a very good semiconductors. Okay, very good semiconductors. We can increase its conductivity. Now let's go back to the pure form. Okay, the pure form. Let's go back to the pure form. Here is the pure form. Now in the middle we have silicon. All are silicon atom, isn't it? This is all silicon. All are silicon. Now in the middle, if we put, for example, this silicon, in place of silicon, the impurities like arsenic. Okay, like arsenic, let me put arsenic here, atom. So arsenic, which is a metalloid, its valency is 5, whereas the silicon is 4, isn't it? So there will be a free electron here, free electron. Now let me redraw it. Okay, atom. However, in the middle we have arsenic. Now we have 1 2 3 4 plus another arsenic atom. From arsenic atom I means an electron. Now it's complete. Okay, now it is complete, but here we have one more extra electron, which we call as, this is electron, free electron is the now it is free electron, which is the majority here. Now this kind of semiconductor is called as n-type. N for negative. Okay, because the free electron here is a negative charge. Okay, here is another diagram. Now we have seen that this is silicon. However, this one is pentavalent, 5 valency, it have 5 valency electron, and here's silicon is plus 4, which is, if we combine that means it is 9, and that means 8 plus 1, so this will be one free electron. Here we will have, so free electron, okay, we see that free electron, okay. This is another diagram also. So this is how it looks. Okay, let me show you another picture. Okay, this is in the energy band. Okay, energy band of n-type semiconductor. So the upper one is, this is the conduction band, and the lower one is, this one is the energy band. Okay, so there is an energy gap here. This is energy gap. In the upper side, we can see that in the upper side here, this one is, there is a dotted lines. This is an also energy level donor, which is called the donor energy level. Okay, so the donor energy level, the donor energy level is about 0.01 electron volt to 0.045 electron volt. Okay, this is a small gap, okay, and this is a donor energy level, and this altogether this is energy gap. Okay, and this, the lower one is valence band, and this, the upper one is the conduction band in extrinsic, in n-type extrinsic semiconductor. Okay, now this becomes n-type. Okay, so this is an n-type semiconductor. Okay, so the majority carrier are electrons here, and also there is another one which is called the p-type. Okay, now let us go back to this. Now in place of arsenic, if we add three valency electron, okay, now let me make it green. Now like indium, okay, indium, it will have 3 valency. Okay, 3. So 3 plus 4 means 7. Now it is deficient in 1 electron. Now there will be a hole here, there will be a gap, there will be a gap here, hole. So the hole alo korong tani chu 3 plus 7 ni bang kham it's one in, so it will be deficient in 1 electron, 7, so it needs 1 more electron. When electron jump from here, and fill it up again, this will, there will be a hole, and when another electron jump from here, then there will be a hole again, it will create another hole here. So a hole will go like this. It will also carries electric current. So now electric current is formed by a hole here. The hole is moving, isn't it? In place of, we can say the hole is moving. Okay, now let us look another picture here. As I have told you, this is silicon for valence C, and in the middle we add now, instead of pentavalent, now it is trivalent, which is 3. Okay, 3 valency. So plus 4, which will be equal to 7, isn't it? So 7 plus hole means it is deficiency in 1 electron. Okay, so there will be a hole here, there will be a hole. So in this region there will be a hole, and if this electron jump to here, then there will be a hole here, and if this electron again jump here, and there will be a hole, and then if this electron jump here, then there will be a hole. So the hole is moving from here to here, so it is responsible for the conductivity. Now the hole is responsible for the conductivity current CM2 lo ni tani chu tiang khan electron poi current CM2 ni thai line, hole po current CM2. So hole are the majority carrier here in p-type extrinsic semiconductor. Okay, this is a p-type extrinsic semiconductor. Okay, so let me show you another picture. So here is another picture, which is the energy bands diagram in a p-type semiconductors. Okay, p-type semiconductor. Now you can see that in the upper, which is the conduction band, which is the conduction band, in the lower one, this one is the valence band. Okay, the valence band, and we can see here there is a gap in between this. This is called energy gap. However, in this p-type, you can see here you can see here this line, you can see this line, this is the acceptor energy level. Okay, before you see that it is a donor level here, donor energy level. However, in this p-type you can see this energy level here, acceptor, which is called acceptor energy level. Okay, so energy level here near the valence band. So in n-type we can see energy level, donor energy level in near the conduction energy, near the conduction band. Okay, so this is how it looks. Okay, this is the energy band in p-type semiconductor. Okay, so this is how it forms. So this kind of extrinsic semiconductor is called p-type. Okay, in this p-type, since hole are the majority carrier, that's why it is denoted as positive charge carrier. So that's why it is denoted as P. Okay, P, positive charge carrier, or the hole. So we made two types. One is N type and another one is P type. So we have two type of semiconductor, P type and N type, which are very useful. And so in both ways, in P type and N type, in P type and in N type, it will conduct. The conductivity is very strong now. So we have a good form of semiconductors now. Okay, so this is how p-type and n-type is formed.